some thoughts that I have regarding perturbative dynamics in ADS. And here I should emphasize there is a certain simplicity here, which this personally I think is sort of unexpected from neural integration you'll see in the end. So the perturbation theory in this ADS is interesting. To me, it's like from two aspects. Of course, the usual aspect is that there's holography, which suggests that precise correspondence between ADS and the CFT. One is weakly coupling, or coupled, and the other is strongly coupled in the neural region that people study. And another connection is that starting with the ADS and consider some productive procedure there, and then we can take the ADS radius to be large, and in the limit, the scattering is expected to reduce to that people are familiar with, one in flat space. So to be more precisely, in these three contexts, we can talk about some physical quantities that are similar. In flat space, we can study the scattering amplitude. In ADS, since it has a different boundary, we can also talk about scattering problems. And the quantity usually tied to that people talk about is the milling amplitude, which is the analog of the scattering amplitude. And of course, on the safety side, we usually study the correlators. And of course, for these quantities, usually we are very interested in what are their analytic structure and properties. For the scattering amplitude, it could have poles, it could also have branch cuts, and the poles usually correspond to the single particle state in the propagating, and the branch cut usually signals the presence of multi-particle state. However, on the ADS side, if we look at the milling amplitude, then frequently we'll see, as we'll also see later on, that this quantity is always meromorphic. In other words, it only has poles, and actually the pole also always form semi-infinite families, always. And for both the single particles, sorry. And for both the single particle state and multi-particle state, actually all of them are encoded in the poles, which is a little bit different from what we are familiar with in flat space. And of course, on the CFT side, both the single particle state and multi-particle state are usually corresponds to single trace operators and multi-trace operators in the large N. But here in this context, on the CFT side, we are always talking about the holographic CFTs. Now, however, although despite of the fact that the milling amplitude are always expected to be meromorphic functions, it's from the previous study, it seems that the quantities are usually very hard to study, especially up to nowadays. The neural knowledge is usually only limited to at most one loop, some simple diagrams. But in this talk, we will see how we can efficiently work with diagrams at arbitrary higher loop level. So the aim of this talk, there are two folds. One fold is that we would like to learn to try to develop efficient and systematic methods for the computation of written diagrams. And as a result, we would also like to see what kind of knowledge we can acquire about the detailed structure of the analytic properties of the milling amplitudes associated to the scattering in ADS. And for the focus of this talk, we'll only look at the very preliminary theory. In other words, the scalar effective series in pure ADS background, and also for the coupling, I'll only assume arbitrary coupling like scalar to some power. I'm not putting any derivatives, just to make the story simple. Now, let me first begin with a quick review of what milling amplitude is. We know that since we are studying scattering in ADS, the isometry there will induce the conformal symmetry on the boundary. And so for whatever scattering, when we view it from the boundary, it always looks like some CFT correlator. And just due to this, it's particularly nice to transform these space-time correlators into a different space, which people usually call milling space. And correspondingly, the transform is a milling transform. And this M is a quantity that we usually call the Main amplitude. Just to explain a little bit the notation here, this x, small x, denotes the boundary coordinates, space-time coordinates, and the delta of the parameters in the Main space. And it actually comes under a certain constraint. Usually each of these delta variables are labeled by two boundary points, and they have to be symmetric, and also they're related to the actual conformal dimension of the boundary points, and they have to satisfy a certain linear constraints. And so in general, here we will also assume that the boundary space-time dimension is sufficiently high, so that we only get this constraint, and usually for given number of boundary points n, the independent deltas are of the number n times n minus 3/2. Of course, we could also study the other case, but that adds in a little bit complication, and let's not temporarily not focus on that. Now, this quantity usually has poles in each delta, and the poles, as I said, will form into semi-infinite families. And this prescription for this counter, Main integral counter, is that every family of poles should entirely sit on one side of the counter. I'll show you one little example later on. And also, just due to this constraint, you can immediately notice that if we try to identify each of these delta as a corresponding Lorentz invariant product of some momenta, and then all these constraints are automatically satisfied. And due to that, we can also try to define a certain quantity, which we also call the Mandelstam variables in the Euro way, in the Euro form we are familiar with for the flat-based scatter. And it turns out that the Main amplitude actually only depends on these Mandelstam variables, but not arbitrary combinations of the deltas.
Excuse me, are you using already holography to declare that what would be a written diagram result is related to correlations of operators on the boundary? That's the formula you've written.
Yeah,
but if I don't want to assume holography, if I start a discussion of empty written diagrams in and by themselves,
yeah.
Is there a statement you could make saying, for example, correlations of n scalars is equal to something like this?
You can just plainly take this purely from the bulk point of view.
This what you've written from bulk point of view literally is a bootstrap type of answer for n point function.
Yeah.
Written diagram.
Purely from the bulk.
And regardless of loops or tree diagram doesn't matter.
It doesn't matter.
Final result must be of this form,
right.
By symmetry.
Just due to the asymmetry of the bulk.
What about crossing symmetry? Have you assumed
if you just work explicitly with the diagrams, then the crossing symmetry is sort of guaranteed, right? Because you're adding up the diagrams. Yeah. So here I'm not talking anything about the CFT for the time being. Actually, not for most of the time.
Okay.
And also, of course, in general, we would like to calculate in detail what this quantity is, and for that we need to use the analog of the Feynman rules, which is designed for the Witten diagrams. So here in particular, we should be interested in what the bulk-to-boundary propagator is, what the bulk-to-bulk propagator is. The bulk-to-boundary propagator is really simple, but the bulk-to-bulk propagator is hard because generically it's like some complicated hypergeometric functions, and it's hard to work with. But nevertheless, there's a very simple representation that we can utilize, which is a so-called split representation. Quickly speaking, this split representation is to represent every bulk-to-bulk propagator as a certain integral of an ordinary product of two bulk-to-boundary propagator. So each of these start from one of the bulk points, and they enter at the same boundary point, and you need to integrate over the whole boundary. And then furthermore, there's a certain other Main integral, which we can call the spectrum integral, because this is really encoding the information about the spectrum you see in the propagator. So that's roughly what this representation is doing. And now, due to this, actually in most of the talk, I will also equally focus on another quantity, which is not the amplitude, but a certain integrand to that prior to all the spectrum integrations tied to all the bulk-to-bulk propagators.
This capital X and Y is not four-dimensional intrinsic coordinate, is it? In
It's not.
ADS.
It's just
It's
a
an embedding coordinate.
No, I'm not.
No.
In this talk, you can totally forget about what specific coordinates I'm using.
But I need to know, is it a point in ADS space?
It's inside ADS.
Inside ADS,
Yeah.
thank you.
Just to distinguish. But
Okay.
here, actually, I'm not working at all with space-time. It's just some preliminary setup. We'll see later on. But just to fully use this representation, it is also nice to focus on a different quantity, which is prior to all the spectrum integrations. The reason is that since this is a certain integrand, it has to be simpler. But the nice thing is that this quantity actually also shares many qualitative features with the amplitude itself, as I will show you later on. So mostly I'll talk about this, but also I'll also use the knowledge for the pre-amplitude to learn about what the amplitude is later. And this n is just normalization apart from the measure for the spectrum integration.
What is the difference between delta and delta underline?
Oh, yes, good point. So here in this talk, I'm going to assume generic data for arbitrary diagram. And so I'm not like assuming the same scalar for every propagator, and I'm denoting them differently. And to distinguish between the bulk-to-bulk propagator and the bulk-to-boundary propagator, I'm always use the plain delta for the boundary points, but the underlying delta for the bulk-to-bulk the dimension of the bulk-to-bulk propagators.
Okay.
Just to distinguish them,
Okay.
to show the structure, but nothing else. And so the main difference between this quantity is that the amplitude will depend on the actual conformal dimension of the bulk-to-bulk propagator, but the pre-amplitude will not depend on it at all, but instead depend on the spectrum variable of that propagator. This is one of the main differences.
What are those G's? More specifically, what is the H minus and plus C dependence of these bulk-to-boundary propagators?
Here?
Yeah.
This is just denoting some the conformal dimension of this boundary points D. But I'm assigning it to H plus C and H minus C respectively. And this H is half of the boundary space-time dimension. Just assigning the conformal dimension for that.
Is it important that the boundary dimension is
Not, it's not. I think you can even assume H to be arbitrary. Given some
Is there a way to fix this problem?
If you plug it in, it might be
I
power
think
saving.
it's actually some
I think your laptop is
computer.
like a power saving. So if you plug it in,
sorry
it's
about
also-
this.
There must be screening.
No, his computer just you can run in a power saving mode.
Oh, yeah.
Where is
I think it's on this wire.
Show it where it is. Yeah, thank you.
Good. I think this is good. Yeah, so just show you the simplest example. If you can just consider a compact diagram, there's only one single bulk vertex, but no multiple propagators, then the pre-amplitude will be as simple as a single gamma function, which is summation of all the boundary conformal dimensions over 2 and minus half of the boundary space-time dimension. This is like the building elements that we are going to use later on. Now, to show you how nice the pre-amplitude is, let's just focus on the tree level. For the tree level, actually, the people have already have a lot of knowledge previously. But here, the nice thing to use the pre-amplitude is that the pre-amplitude actually for tree level diagrams are just ordinary products, very much similar to the trees for flat space scattering. So this product will be a product of elements derived from each bulk-to-bulk propagator. For each A, we have the spectrum variable and the corresponding metal stand variable as A. And then there's this simple factor. Here the notation, the plus minus just indicates that actually this is a product of two gamma functions, each with one choice of sign. This is going to be the notation I'll use frequently. And then later, furthermore, for each bulk vertex A, with capital A, this delta A will denote the summation of all the conformal dimension for all the boundary points directly tied to it. And then I'm assuming that there are altogether R bulk-to-bulk propagators incident to this vertex, and correspondingly there's the spectrum variable and the metal stand variable, and it takes this integral representation. But usually it's more convenient to use a different notation. So here, this gamma, again, this is a product of a bunch of gammas, each with a specific choice of a sign. And this product of gammas will actually encodes all the poles contained in this function. And then whatever remaining thing is a pole-free function, which we'll call CA, which is named as a correction function. And usually it's very important to learn about what the pole is, but for this we can roughly understand it as just some coupling.
Can you draw a diagram, written diagram for this? Is it a blob with n external lines?
Yeah, so usually for this single bulk vertex A, there's a boundary, and then there could be many bulk-to-boundary propagators here, emitted from this vertex. And I'm calling the delta of big A to be the summation of every conformal dimension for every point, the whole summation. And then furthermore, there could be many bulk-to-bulk propagators connecting it with other bulk points and labeling them from 1 to R.
And where do they end up? I have to go to the
There
bottom.
could be some other vertex that, like say B, C, and then they may further emit other bulk-to-boundary propagators.
I see. So this is a building block you've completed for us.
Yeah, this can be rigorously derived. And in order to learn to write down the pre-amplitude, say for this diagram, then all what you need to do is to collect all the boundary points for that bulk vertex. For each bulk vertex, you write down such a function, or the product with the coupling.
And then solve them together.
Just take the ordinary product of everything. Of course, also for each tree propagator, you write down these small vectors. This is everything you need here. So this is sort of like in strict analogy with the tree amplitude for flat space scattering when you learn them in the momentum space.
Why is there an integral? Oh, because it's the fluid?
Well, this is just because the function, the entire function is complicated, and I'm writing it in a convenient way. There's no other purpose. Yeah. Actually, one of the integrals can be trivially done, but it breaks the symmetries rather vivid here. In general, this function the integral is hard to be performed, but nevertheless, you can learn precisely what are the poles of the resulting function. And that's what I'm writing down here. And then you can collect whatever remaining into some other function, which is purely free of poles, which you can roughly understand as some coupling local to one of the vertex. Also, you should notice that each of the data entry here are all local to the particular vertex. And so this is purely a local rule from the diagram.
How many of the lines are there that go to the boundary on the left?
It doesn't matter.
Doesn't matter.
You can put
But the other one is R.
Yeah, you're assuming R, but this R can also be arbitrary.
I know, but given R, the other one can be another number.
Yeah, some
Okay.
other arbitrary number.
Okay.
Even just a single boundary property doesn't matter.
Okay.
So this is about the pre-amplitude. And then, of course, in the end, we would like to go to amplitude. And here we would need to see how they are related together. The two objects, as I said, are related by the spectrum integrations. Here you should notice that in the spectrum integration, there are additional poles from the normalization factor. And so the actual dependence on the conformal dimension of the boundary propagators will enter via this spectrum integration. And correspondingly, there are poles in the amplitude. And this pose actually has to emerge from the spectrum variable in the following way. So every time when you want to study some pose resulting from an integral, you need to care about the situation where the integral contour is pinched by original pose in the integrand from two sides, such as the contour cannot be moved. So in this case, you encounter a singularity. And here particularly, we can verify that the singularity is a pole.
By pinching, you mean you bring two dots together, 2 points?
Yeah. They come
towards
together.
the line. That's what you mean by
Yes,
pinching.
yes. So there's no way to deform the contour to avoid the pinching. And then locally there, the integral will produce a divergence, and that's a signal of a singularity. And in particular, in the Manet integral setup, you can further verify that this singularity is actually a pole, but not a front cut. But I'm skipping all these details. I'm directly telling you that you can basically learn about what the poles of the integral are by looking at how the contour can be pinched by the original poles. I hope this is clear. Do anybody need to?
What if you pinch to gamma functions?
Like a pole here and a pole here?
Yeah, from gamma functions.
Yeah, in principle, you should also worry about that. But the good news is that when you think about that integration, there are actually additional zeros from other parts of the integrand that kills the pole. So that doesn't matter.
So generically true.
It can be, yes.
So you only have simple poles,
Yes.
you're saying?
Yes.
Mm.
To be rigorous, the story is actually a little bit more subtler, but I'll just simply say this. Unless you want to know details later, we can talk about it later. Yeah, but this is basically how the pole of the amplitude emerges from the pre-amplitude. And it's in a very simple way because here you can see that these poles are actually encoding the actual physical poles. So here from this gamma function, you'll see that there's corresponding poles at the location, and the corresponding Mandelstam variable in this channel takes the value of this single conformal dimension plus 2m. This is like encoding the information about the states for this single trace operators in the corresponding OP expansion you see in this channel.
But the theory only had scalar field. What's the meaning of that cut? I mean, you don't have infinitely many states in the theory.
Well, in some sense you do, because there are all some descendant states from a single primary.
But that's again CFT intuition you're using.
That
What about
is-
from ADS field theory point of view? I'm given a scalar
Well,
field.
in ADS, you can still think about arbitrary high energies in the propagating states. But it's just
So it's not the lowest energy state then. You're acting with
Yeah, it's not always lowest energy state. This is one of the main difference from
So
the
let's say do on this. You have a single scalar field with a given lowest energy. Let's say fixed lowest energy E. What this refers to, this M, is it is the states you obtain by acting with the energy raising operator on this state.
Yeah.
It's not a new scalar field. so
Yeah,
to
it's
speak.
in that
It's
sense.
the
yes,
excitation
yeah.
of the given scalar field.
Right.
Okay.
Yeah.
Okay.
In some sense, this is expected because here the setup is like you're inserting operators on the boundary. You're not assigning operators with a given fixed energy, and so in the bulk, there's no momentum conservation to constrain this to be of a particular energy state. That is sort of expected. Anyway, every time when we see such a pole, diagrammatically we can roughly related to a certain cut of the diagram by cutting one of the tree permutations. This is in very close analogy with what you see in the flat space case, nevertheless. Just diagrammatically the cut. The correspondence between
If
the
somebody gives you the
cut.
answer for this cut, could you go back, reconstruct the full amplitude from it?
That's actually what I'm using.
You will be using?
Yes.
I see.
So just to extend this intuition a little bit, we can actually apply this correspondence between cut and a certain diameters of poles to arbitrary diagrams we use. So here by a cut, specifically we will mean that we imagine draw something to separate the original diagram into two parts, each of which has to be connected, connected diagram. This is what we call a cut. And of course it has to separate the boundary points into two groups. And now, usually when we talk about scattering amplitude, let's just stare at this particular two-loop diagram. When we look at this, it only has a non-trivial S channel, but the T and the U channel are sort of trivial. So the S channel, we could see 4 different types of cuts, 2 associated to a 2-particle state, and the other pair are each associated to a 3-particle state. And correspondingly, if we think about this scattering amplitude, then we should expect 4 different bunch cuts. Each starts with the lowest energy state of the multi-particle. Right? And so, just by analogy, we could hope that if we instead study the corresponding Manin amplitude, and then we should see the presence of all of these 4 families of poles, each encoding the lowest energy state and all the excited state. That's some intuition that seems to apply. However, of course, we need to verify and look in detail whether this really holds and maybe try to analyze some other properties. And we are going to see in the end whether this is really true or not. And there's a little bit surprise in it.
For a single particle exchange, you explained what it means, that cut. I understand now.
Yeah.
But now we have 2 particles, 3 particles being cut in the intermediate channel. What is the intuition for that? I mean, should I group theoretically take tensor product of 2 irreps of ADS and decompose it into?
Well, for the simplest thing, you can imagine that take this as plainly as a scattering process. And then, of course, there could be configurations such as the total energy is high enough so that all these states could be real particles. And then just by optical theorem, there has to be very signally some singularity of the corresponding amplitude. Right? I know this is a bit rough, but that's.
In the case of 1, 2, the first
Yeah.
cross, that one,
Yeah.
the intermediate state is a 2-particle state, is it?
Yes.
I should think of it as 2, 3 on-shell particles being exchanged.
Yeah, you're
Is that the point?
Yes.
Okay.
Yes. Of course, in flat space, you are further need to integrate over phase space, but that sounds like it. Yeah. So in this talk, most of the efforts will be devoted to verifying, to answer this question. So in order to answer this question, we need to have machinery to help us effectively learn about diagrams of arbitrary loops. And this is going to be the next section where I'll only mainly talk about the construction of the diagrams. So here there are listing some basic ideas here. So as I said, here we will mainly focus on the pre-amplitude. After we get a good knowledge of that, we can further study the properties of the many amplitudes through the spectral integrations. But just to build up the pre-amplitude for each specific diagram, we are going to use some new ideas. First of all, since the diagrams are characterized by loop levels, so here, an efficient way to do the computation is, of course, after we do some simple calculation of some simple diagram, we would like to reuse that knowledge in constructing even more simple, more complicated diagrams. So here, it is better that we find some sort of recursion relation among these diagrams to help us do the computation. And then secondly, since we are defining in Manin space, actually it could be ideal that we are able to perform our computation solely in Manin space, but to forget about space-time. This is a second point. One of the advantages is that, just to remind you that the spectrum variable integrals are actually also many integrals. Once we have some representation of the pre-amplitude in terms of many integrals, these integrals can be combined with the spectral integrals so that everything are put in the same framework and will be studied systematically. And the third thing which is going to be important is that as we said, that the many amplitude, actually also the pre-amplitude, is always expected to be meromorphic. And so they always has poles. If I'm just giving you some arbitrary function without telling you whether this is from a loop diagram or tree diagram, just by staring this poles, it's really hard to distinguish whether this is come from a tree or a loop. In other words, this is telling us that for arbitrary diagrams, actually if we look at this amplitude, effectively we can always think about it as being some tree amplitude. And I'm going to show you how to exactly do this situation. So the basic ingredients, as Jürgen also commented previously, is that we're actually going to use this split representation to turn a pair of boundary propagator into a new box propagator to create a new loop in order to induce the recursion between different diagrams. This is the basic idea. And so here in particular, if we want to start some studies on particular diagram, we are going to assume a single diagram for which we assume we know it completely. And so we can even assign a particular conformal dimension to a pair of its boundary propagators, and then further identify the two boundary points, integrate over the boundary, and then if we are looking at the amplitude, we further do an integration in correspondence to its spectrum variable, and introduce the actual conformal dimension.
There on the left side diagram, it has like physical dimensions, which means that it's not really an amplitude, right? It's something like a shell object. H minus E, it's like a physical dimension, so it's not really an amplitude.
Can't there be two different guys? Those dash, I guess you are saying in a physical, why can't they be physical? H plus C at H minus C? Are they physical bound-to-boundary propagators? Those dashed lines on the left?
These are actual bound-to-boundary propagators.
Are they physical? Is this a good written diagram?
Why not?
So C is...
Of course, if you ask whether this satisfies the unitary bounds, in general, no. But after we get the amplitude, we can arbitrarily do analytic continuation to assign anything you want.
But for example, you have like massless theory, you know the amplitude for fixed dimensions. How would you continue to any dimension?
Okay. Okay. In that sense, I would say you're doing something a little bit non-physical.
So you sort of need to know like how to analytically continue your vertices of shell.
Sure. This might be important later on if you care about some specific theory, even involving spinning particles and non-derivative commutation, non-derivative couplings. There it might create some other subtlety. But here, let's just be satisfied with it because this is a simple setup. Yeah. Yeah. In general, it may cause a little bit subtlety that we have to take care. That's true. So everything good? Now, of course, this operation itself is some operation in space-time. And as I said, here we would like to forget about it, but try to interpret this whole construction as an operator acting on the original Malin pre-amplitude to give us some new pre-amplitude. So every operation here are actually purely performed inside the Malin space. This is some formula that is derived. I'll not tell you specific details about the derivation, but in the end, what you would expect from this loop creation operation is that you just basically take your original amplitude, you multiply by a certain kernel relating the original Malin space and the new Malin space. But here, pay attention that the Malin space for the old diagram and the Malin space for the new diagram are completely two different spaces. And so, in general, we are assigning some kernel and integrate the original amplitude against it and the integration is over the entire original Manin space. The counter is the same counter as we studied before. And the kernel actually takes this simple form. It's just a product of some beta functions. And the thing to be stressed here is that actually, in order to do this, the original space undergoes additional constraint. That's a very simple constraint due to the identification of these two boundary points. Here, I'm assuming that the new diagram has endpoints, and so the old one has two extra ones, which are labeled as 0 and n+1, respectively. This formula is actually applicable to arbitrary diagrams. So here I'm not specifically mean that this is a particular scalar diagram. You can actually assume you can do it as long as the boundary point is some scalar boundary. But of course, in general, this formula can be a little bit complicated because the dimension of this space is pretty high, and so this may not be quite practical. In order to make the construction practical, actually we could think about something simpler by the intuition that we know this Manin amplitude only depends on the Manin space via the Mandelstam variables, which here, as you know, that's HC. It's not an arbitrary dependence. And so we could imagine that the integration operation is actually only integrating over the Mandelstam variables. And so all these are independent variables, and the kernel relates the old variables with the new one, which I denote as. Here there are also some small c variables, which are also Mandelstam variables, but not seen in the old amplitude. I'll tell you why. So the reason that we also want this is that we want some useful formula, so that this kernel still maintains to be simple. If we can also just forget about this, but if we do this, then the kernel has to be complicated. And then in the next few slides, I'll tell you specifically about what this kernel looks like. Actually, it turns out that there's a specific choice of these Mandelstam variables, such as the kernel will also follow certain diagrammatic rules. So as I said, we are going to construct our higher loop diagrams by recursion. That means we are going to start from some pre-amplitude, and then first glue a pair of points on the boundary to create a one loop diagram. Here it is a triangle. And then in the second step, we further glue another pair of points to create our target diagram. This is going to be our working procedure. And we already know very well about this starting point because this is a pre-amplitude. And from what I told you previously, the pre-amplitude can be simply written down as a whole bunch of products. So this is the starting point. And here I'm using the hoping this is clear. I'm using the U variables as the Mandelstam variables for the tree diagram, and also later on T variables for the Mandelstam variables of the one loop diagram, and then finally the S variable. So the first for either of the construction here, the first thing that we should do is to look for a certain maximal chain of OPE channels. What this means is the following. So start from some given scattering procedure, whatever thing this is. Of course, from the boundary point of view, we can think about doing OPEs one by one, a whole sequence of OPEs. For every OPE, we want to separate one of the, separating this pair of boundary points that we are going to glue on two sides. And we also want the set of OPEs denoted by these blue lines to be consistent with each other, so we can do them one by one sequentially. And what this leads to is that from the original scattering procedure, after we do all these OPEs, we can imagine we create an effective train diagram, where each node corresponds to one of the region, which may contain some of the boundary points. Okay. Of course, we cannot include in the train some OPE channels like this, even if the amplitude allows it, because this is not consistent with the other OPE channels in the sequence. And we also want to do it maximally, so that after we obtain this diagram, there's no other non-trivial OPEs that we could do further to add into the sequence. this is going to this first step, that a given maximal chain of OP channels will effectively induce effective chain diagram, which is a pretty special class of tree.
How hard is it to find a solution to this problem?
It's not hard at all. We just focus on some specific diagrams. And then basically every time we look for OPE, it's, in other words, we are looking for a cut along by the diagram. And then we just collect the cuts that are consistent in this sense.
So there are no cuts that you can make in the diagram that are not valid?
Yeah.
Okay.
But the difference is that in a single channel, usually it allows different cuts. But here, even there are different cuts, we are thinking about we are not the same thing because it's the same channel. Yeah. Of course, most generally, you could even imagine that after we obtain this maximal chain of OP channels, we can do further OPEs. But then those OPEs have to at most create some additional branches that grows out of this chain linking the two boundary points to be identified. This is the more general case. So here in the following, let me show you one particular example. So in the simplest setup, we'll start from a tree diagram. And from this logic, actually for a given tree diagram, the corresponding topology diagram is nothing but the tree itself, which is easy to understand, right? So that goes back to this example. In the first step, we are going to glue this tree into a triangle diagram according to this picture. And then here I'm going to introduce some notation. So first of all, you see these big C variables, which are actually the method variables observed by the original amplitude because it's tied to each of the tree propagator. Right? That is basically PC here. It's usually U5. And then furthermore, I'm assigning some C variable. Here, these channels are actually not the channels observed by the original amplitude, but as you easily see, after we do these points, this becomes some natural channels observed by the new one-loop diagram, because it separates the diagram into two connected parts. I'm going to enumerate all such channels and label them. I'm labeling this big C by a particular A. So first of all, here on the chain, I see some vertices. I'm going to label them in the sequence, and then label the C variables accordingly. And then furthermore, for each small C, I'm going to use two labels, one denoting the closest points on the left and the other for the closest point on the right. And then for the new diagram, there's a corresponding new variable for the new amplitude. These are the variables I'm going to use in the recursion relation. And now, correspondingly, in order to construct the kernel, there are actually three corresponding rules. One rule is tied to each of the vertex on the loop. Another rule is tied to each pair of points on the loop. And we need to enumerate all of them. And then there's a third rule tied to each of the vertex in the additional branch growing out of the loop. I'll not say details about this. This is something that you can just grab and apply. And then substitute the corresponding name here to be similar using some other names. And then you can read out the corresponding kernel directly from the diagram. So there are three vertices on the loop. From this rule, you have three terms, vectors, and then there are three different pairs that you can choose. And then from the second line, you read the other three. Each of these are beta functions, standard beta functions. And then there are additional vertices in the branch, and so you just write them accordingly.
How many loops do we have here? This is self-energy.
This itself, we are starting from a tree diagram to build a one-loop triangle diagram.
One-loop triangle diagram.
Yes.
Three-point function with one-loop correction.
No, actually, here it's a 6 point one-loop.
6-point function, one-loop correction.
Yeah, there's point 1, 2, 3, 4, and then the two points labeled by 6 plus minus, which we are going to glue to create the two-loop breaker. So at this stage, it's 6 points.
So you're gluing the 2 points below.
Yeah, we are starting
Those
from
two.
a tree which has 8 points,
Yeah.
but we glue one
You
pair.
glue to one pair.
Yeah.
And this expression in the rectangular box is supposed to capture the singular part of the whole thing, the whole diagram.
No, no, no. This is the entire expression for the integration kernel. This kernel.
So
We
I'm
already-
supposed to plug it into that integral,
Yes.
and then I get the full answer,
Yes.
not just part, singular part.
Yeah,
Okay.
the entire full analytic expression,
Mhm.
although it's an integral expression, just for the one loop pre-amplitude.
And 0 is the tree diagram from which you obtained this, I guess.
M0 is the, where is this? Oh, sorry. M0 is this expression.
The tree diagram,
Yes.
before you glue.
Yes. That's M0, and then the formula in this box is a K that allows you to go from the original tree amplitude to the one loop amplitude pi to the 6 points triangle diagram. The full analytic expression, although it's an integral expression.
It's not for the faint-hearted, I would say.
Well,
It is not for the faint-hearted. Even it sounds very innocent. You just identify 2 points, but that innocent-sounding operation
I don't know.
is quite an affair. Okay.
Well, if you think that this expression is too complicated, or at least too huge, I will assure you that actually to do analysis with it is not that hard as you could imagine. Although I'm not in detail in the topic, so we can run later. So this is some integral expression for this one loop. And then for the second loop, we should start from one loop diagram and then apply the logic as I explained here. So here, we are going to glue these 2 points, and then there's a loop in the middle. But then we see that this loop again allows a maximal chain of size 2, which is this channel and this channel. It doesn't matter whether you cut this 2 or this 1, they are the same channel. So just by this 2 channel, it induces a chain of with 3 knots. So it's basically like this diagram. And then you just apply the same rule and write down the expression.
Do you have a tadpole coming out of this? Tadpole?
No.
No tadpole.
And again, the whole expression in the box is exactly the kernel you are going to use in going from the one loop pre-amplitude to the 2 loop pre-amplitude, as shown here. So to summarize, we already know what the tree pre-amplitude is, and then in the first step, we are going to use the kernel read previously, and here there are the original U variables tied to the original diagram, many space, and here altogether we find there are 7 U variables that we need to integrate. All of these are independent, so they're independent many integrations. And then from the 1 loop to 2 loop pre-amplitude, in addition, we find 5 T variables that we need to integrate. And then further, if you later on want to study the amplitude, there are 6 spectrum variable integrations tied to each of the 6 ball-to-ball functions. So these are all the integrals that are left over. In general, all these integrals left over are non-trivial to do, in the sense if you want to directly apply some node formula to write down some analytic expression for the result, it's impossible. Nevertheless, there are some nice things we could do. First of all, just due to the fact that this whole expression for either the pre-amplitude or the amplitude are fully based on the standard Malay integrals, that means as long as there's no UV divergence tied to the scattering, then this integration, numerical integrations are in principle easy to do, purely due to the fact that the integrals are just product of beta functions, and so we expect that in the infinity, if there's a very sharp drawdown.
The silly question, if I have phi to the n interactions like you told us at the beginning, phi to the n, contact interactions, can we intuitively expect that if n is greater than 4, there will be divergences? Just like in flat space, we know that to be the case.
That's
right?
what people usually think. Because you could imagine that there's a certain region in the integration where only the local, the very local part of the ADS is important. And then you can zoom in out, and it effectively looks like a flat space. And that's the source of the
In fact, when I say the drum, I don't even need to go far higher than pi to the 4. Even pi to the 4 is divergence. It can be normalized away.
Yeah.
Question, do you have such divergences here?
Frequently, if you don't care about specific conversions, then you would definitely encounter that. So that's some general question that people have to answer about this UV divergence. Here, let's temporarily be blind to it.
So your comment only applies to the so-called super renormalizable theories then? Finite ones.
Yeah.
That's fine. Okay.
Yeah.
Okay.
But one of the nice things here is that even if the amplitude study is expected to be divergent, it turns out that I think it's usually in general expected that the pre-amplitude remains to be finite. And the divergence will only enter from the spectrum variables. That's the expectation. This is some estimation. I'm not saying something concrete. This needs to be investigated further.
But you do believe the first two integrals that you wrote here are finite?
Yeah, it has to be finite.
Isn't that straight? I mean, you took trees and closed loops and integrated it.
But you see that I'm postponing all the spectrum variables to the end. And every integral there is encoding tau introduced in the spectrum to each of the property. Yeah.
That those spectrum integrals still have the loop integral in the
So this is something that you cannot avoid, but the moral here is that we can separate the question and then postpone those issues to the end, and extract some still useful information about the study.
At the very least, the only regularization we would have to do is the last integral.
Yeah. That's
Still way better than
That's what I expect. Of course, as I also said previously, if we really try to get some analytic answer in terms of familiar functions, in general, it's pretty hard, and we cannot expect that. Although sometimes in special situations, the answer could, in principle, be reduced to some known functions, or this is something that does not play a role in general. So what we can do? Still, as I said, since these are just many integrals, standard many integrals, actually this fact guarantees us that either both the pre-amplitude and the amplitude are always meromorphic functions. And now once we know they are meromorphic functions, the questions are pretty clear. We want to know where are all its poles, about the existence of every pole, and where are their specific locations. And further on, we would want to know the local nature of these poles, what's the order, what's the corresponding residue, whether we can write down the exact expression just for the residue at each pole, such questions. Now, here, I'll just merely say that there is a systematic method which we can apply in answering all these questions. All these questions, but I'm not going to tell you in detail about what this method is. In the rest of the talk, I'll just basically focus on the first question, which is to address what are exactly the pole structure for the pre-amplitude, and also for some information about the amplitude. And I'm going to show you that actually, regarding the pole structure itself, there is certain universality in the structure. And this is going to be the main purpose of the talk. And after we know what the structure is, actually, this analysis will also make it very simple to answer the remaining questions. But I'm going to discuss about that. So first of all, let's focus on the pre-amplitude. Here I'm basically just summarizing the result for you. It turns out that if you just focus on the pre-amplitude, the pole structure will follow some very simple diagrammatic rules. First of all, there's a vertex rule, which tells you that every time you just focus on a particular top vertex, associated to it, there is a whole set of families of poles that you will observe in the pre-amplitude. Again, this plus or minus sign just means that different families each with the specific poles on the side. So correspondingly, like in this diagram, we see 6 dot points, and for each of them, there's a certain families of poles that we could see. And then second, there is a certain generalization to the propagator rule for the tree diagram. But here we have to generalize this to a certain channel rule. In other words, every time we focus on a specific channel, in this channel we enumerate all possible cuts at the start. And then for each specific cut, we should write down a corresponding set of poles. They are expected to be present again. So here, this diagram only allows non-trivial dependence in the S channel. And then in the S channel, there are 4 cuts. 2 for the 2 particle states and another 2 for the 3 particle states. Actually, here we also need to include the trivial channels, which separate one boundary point from the rest. And so here there's a channel for delta 3, and that's for the 3rd point, and also a trivial channel for the 4th point. For each of them, there are 2 cuts allowed, one for the 2 particle state, another for 3 particle states. This is like the encoding some decaying of a single particle. Sorry. Apart from this, there are some new things. So we see that there are loops here. In addition to the vertex rule and the channel rule, we should also further consider all possible contractions of the loop, existing loops. Every time when we contract one loop, in principle, we would expect a new bulk vertex to emerge. And for each of these new bulk vertex, we should also apply the previous vertex rule for this new emergent vertex. So here there are 3 possibilities. In general, we would also worry about the so-called generalized bubble rule, but this just corresponds accounts for some subtleties, which we can forget about. It doesn't apply in this case, just to make the story simple. So let us collect all these results that we read from the elements in the diagram. It turns out that from this initial calculation, all these poles are present in the final answer, except for these 4 guys, which are lighted marked blue. They turn out to be absent. And we need to understand how different they are from the remaining poles. Actually, it turns out there's a very sharp criteria. Roughly speaking, since the time is limited, I just quickly say that from this whole collection of poles, you could imagine that these are poles from some function, certain function. And but from this function, we further do certain C integrals or delta integrals. And if we do that, then in principle, we could see that these poles will emerge from the C integrals or delta integrals from other existing poles. For example, for this 3-cut pole, titled C1, C3, C2, C5, we could start from this pole here with C1, C2, and this pole with C2, C3. And then, just due to this C2 integral, we name this C2 variable, and the poles will be of this form. So they are emergent, and we call these poles conflict poles. And then there's a sharp conjecture in general. So in general, for arbitrary scalar Witten diagram, in order to understand the entire pole structure of the pre-amplitude, we first apply these 4 rules, collecting all the poles. And then based on the poles that we collected, we just figure out which poles are conflict poles. And then we eliminate all of these conflict poles. The remaining poles are all the genuine poles of the given pre-amplitude. This is expected to apply for arbitrary scalar Witten diagram with arbitrary configuration.
And again, once I have the pre-amplitude determined, I can go on to calculate the full amplitude.
Yes,
Okay.
that's going to be the next topic.
Okay.
I'll just very quickly talk about it.
So where all these rules come from? It's just summary of experience, right?
Yeah, purely empirical summary. There's no proof, at least I haven't found it. But I've verified this to many non-trivial 2-loop diagrams and even high-loop diagrams in a very special class. So there's already a lot of evidence supporting this.
Do you know what's happening diagrammatically when you have this composite pole loop?
Maybe I'll show you later on. It may be apparent later. So next, we could study the pole structure of the many amplitude. Here for the amplitude, I'm now going to study arbitrary poles, the entire pole structure. but I'm only going to focus on the poles that actually depend on the minus time variables. Those are the poles that we are mostly interested in. And then there's another sharp statement about those poles. So here, as I said, this diagram only allows poles in the S channel, so we just focus on that. And previously, I told you that actually the S channel allows altogether 4 cuts, but as you already see here, there are 2 set of cuts which are ruled out by the completeness. And so those poles corresponding to the 3-particle cut are not there for the pre-amplitude. And so we have to distinguish between 2 situations. The first situation is what we call the minimal cuts, and they're defined by the fact that the corresponding poles in the pre-amplitude are actually present. So there are these poles in the pre-amplitude. And then it's in very close analogy with what you see for the pre-amplitude. In order to produce the corresponding pole in the amplitude, all what you need are just the C1, C2 integration, the variables tied to the propagator that you cut. And again, the poles are present due to the pinch of the C1, C2 contours by these original poles. These are called minimal because in order to produce these poles, we only need the spectrum variables tied to the propagator that are cut. But all the other spectrum variables are irrelevant. So that's the logic for the definition. It is clear? Okay. And then let's compare. So there's another 2 cut which corresponded to the 3-particle cut here. But it's very tempting that we want to produce this cut from the C1, C3, C5 integral by the analogy. But in order to do that, we need such poles in the pre-amplitude, but they are not there. However, the nice thing is that exactly due to the completeness of these poles, although they are absent, but they can be produced by other spectrum integrations from the poles that do exist. And so these poles cuts of these poles are called non-minimal because in order to produce these poles in the amplitude, it needs more spectrum integrations to be responsible for that. This information are telling you, in principle, how you would want to calculate the residue. This information are there. Now, it turns out that when you do compute the residue, assuming that these poles are there, from specific computation, you will see that these non-minimal poles turns out to be completely absent. So in the actual Malin amplitude for this 2-loop diagram here, although from the diagrammatic intuition, you expect in the S channel the presence of all these families, 4 families of poles, it turns out that both these family of poles corresponding to the 3 cut are absent. You don't see them at all. And so correspondingly, there's a general conjecture that as long as you consider diagrams that does not contain any subdiagram, which is a generalized bubble, again, this is some subtlety that temporarily you can just forget about. For all those diagrams, in particular this one, the only families of poles in the Mandelstam variables that are present in the Malin amplitude are exactly in one-to-one correspondence with the minimal cuts.
Minimal cut doesn't mean necessarily 2-particle exchange.
Doesn't necessarily.
Okay.
But here you are also diagrammatically, you could also see what's the connection between the minimal cut and the non-minimal cut. For example, if you look at this one and this minimal one, they are connected by a 3-point vertex, which is actually providing information here in order to go through. So actually, this is a sort of surprising because it seems to be in contradiction with what we would expect from flat space. And we do know that if we treat this diagram as a flat space scattering, and if we compute the scattering amplitude, we actually expect the Browns cut in correspondence to this 3-particle state, as I said previously. And usually people expect that when you carefully take the large radius, ADS radius limit, you want the Banach amplitude to reduce to the flat space scattering amplitude. But then this puts a sharp challenge on how exactly those branch cuts has to be merged. And this is a question that I think.
You started saying branch cuts up in there. I thought we were talking about poles.
Yeah, for the Banach amplitude it's poles.
Yeah.
But say if you consider just a bubble diagram, it has a family of poles. But when you carefully take the flat space limit, you expect this pole to condensate into a branch cut. And that is exactly the branch cut in correspondence to the two-particle state. And similarly, you would expect things to hold here. But naively, every time when you want to see a branch cut in the corresponding Banach amplitude, you would prefer at best the situation that there's a certain corresponding fragment of poles already present in the Banach amplitude, so that they directly compensate into the branch cut you expect. But here, these poles are absent, and so it's becoming very confusing how you would expect that if the proper limit, the corresponding branch cut can emerge.
Is this still an open problem?
It's an open problem.
Why can't we declare this to be a fatal test of your proposal? In principle, could we not say that your proposal is fair at this point? Because it does not give the right answer.
Already there are explicit examples where you see that these poles are indeed absent. So at least you should answer why they're absent here, but then they're present.
Tell me facts.
So actually,
No, it's a proposal.
no.
These are
Even
facts.
about this diagram, it's a fact. This is a proposal for arbitrary diagrams. But for many specific diagrams, it's a fact. It's a calculational fact, a calculational observation.
But if it is a fact, but it doesn't give rise to the correct flat space amplitude, is there not a problem in what it calls?
Well, then you could also wonder whether we should take care about how to take the flat space.
Right. I don't think there's any proof that it can't give rise to the correct.
There are some attempting proof, but at least personally, I'm not quite satisfied with that.
Requires alternative thought.
Okay, so we'll put the blame there on not doing the limit right.
Well, another lesson I would advocate here is that these observations are sort of telling us that we might be cautious and think hard about to what extent we would accept that the Banach amplitude are the analog of scattering amplitude for the AES scatter in the Euro sense. But just let me point out another small, maybe conceptual contradiction that is true. Can I turn on the light?
Should we wait until the end?
Oh, sure. Sorry about this. Yeah. Well, there's nothing left. I guess I don't need to read the summary. Or maybe just to be quick, here we are talking about the construction of the diagram arbitrary loops, and then further I'm telling you, I'm not telling you how to use that resulting representation to exactly the analytic properties, but I'm just presenting you some basic observations about some universal structure that you expect to see for scattering and arbitrary loops, which are sort of a rule. So, thank you.